So I'm going to tell you a little bit about the work that we've been doing on cavity magnonics. This goes back to some discussions that already happened yesterday. Like other speakers, it's always a good idea to do acknowledgments first so that you don't forget later. So these two folks did most of the work that I'm going to tell you about. Here's my group. I want to acknowledge great collaborations with Zeke Johnston-Halperin's group at Ohio State University. They did all the materials growth. And theory collaboration with Michael Flatte at the University of Iowa. Okay, so my research group at Cornell has a very kind of split personality. Historically, we've worked on sort of magnetism and condensed matter physics, and that's roughly half of the group. Growing materials, studying them using different microscopy techniques, which includes scanning NV, but not only. And then the other part of my group thinks about sort of quantum information science, I'll say in quotes, hardware, because it's mostly based on color centers and wide bandgap materials, diamond being the prominent member, but also some other material systems. And these were really quite distinct research programs. As Natalie mentioned, COVID gave us all a pause, and we kind of sat back and thought, oh, I should try new things. And so in my case, that led to the research that I'm going to tell you about now. So the inspiration for this research is this idea of hybrid quantum systems. And so to explain why I think this is interesting, let me just point out what I think of this kind of basic unit of cavity quantum electrodynamics that has been pioneered in AMO and the superconducting circuit community, where the basic unit is always a pair of things, not just a single thing. The qubit gets all of the press, right? Some two-level system. This is our basic unit of logic. It provides a nonlinearity in these systems. And there's many possible qubit types. You could have a superconducting qubit. You could have a quantum dot, as we heard yesterday from Peter Lodahl. And you can have a spin. So that's great. But as we know from our superconducting circuit colleagues, in order to do things like even read out this qubit, oftentimes you have to pair it with some type of harmonic oscillator, right? So this enables the dispersive qubit readout. It could be an interconnect, connecting different qubits together. It could be a quantum memory, because some resonator types have coherence times that actually are much better than the qubit itself. And in principle, this resonator is often an electromagnetic resonator or an optical cavity, but it could be really any kind of harmonic oscillator in principle. And there's work exploring acoustic kinds of resonators, and what you'll hear here is about magnonic types of resonators. And then you can extend this paradigm further. In a hybrid quantum system, you can now think about coupling to some different kind of qubit or resonator in which you have totally different degrees of freedom, with the idea that you want to take advantage of the interesting properties and new physics enabled by a different kind of a platform. All right, so where do we start? We always start here. We start with the simplest possible system that we can engineer, so that it's some model system that we can use to figure out all the couplings and work things through. So in cavity magnonics, this is a microwave resonator, so a regular electromagnetic kind of a cavity, and then we need some very low dissipation magnet to make it interesting for the quantum limit. And this field of cavity magnonics is not new. It has existed for quite some time. This paper by Oni Sokal and Michael Flatte goes back from 2010. This was already mentioned yesterday. There's a number of review papers that I encourage you to look at. Some nice work. And there's a lot of possible applications for this sort of cavity magnonic systems that has been described in terms of, so for instance, sensing of magnons, introducing non-reciprocal effects into, for instance, circuit QED. And we already heard a great talk yesterday about how one can do that just by engineering phases. But of course, magnetic materials themselves break time reversal symmetry, offering that very interesting possibility in a different way. Lots of interesting work on non-Hermitian effects that can be present in these kinds of systems. So there's a lot of rich physics that can be present in this very simple system in which we just have two coupled harmonic oscillators. This gives a basic sort of picture of the cavity magnonic platform that we have. So we have some simple kind of electromagnetic resonator. Here it's just a lumped element LC resonator, and then some kind of magnetic excitation magnons. They each have their own damping rates, and they have some coupling between them. Okay. So, the interesting regime of cavity magnonics, where most of the phenomena that we wish to study takes place, is in the strong coupling limit. So let me just say a quick word about this. This isn't new to you, I'm sure. But the basic idea is that the coupling between these two systems must exceed the damping rates, or if you prefer, the line widths of these two individual systems. And if you do that, then sort of you get the separation of modes that you expect even from classical physics, and you can get this kind of a picture from two pendulum and a spring between them, right? That's totally classical effect. But within this region, they become hybridized. So the excitations of this system are not purely electromagnetic, and they're not purely spin. They're some linear combination of these two systems. Sometimes people also put this in terms of a cooperativity, which is just a ratio of these quantities. And these are all, again, obtainable using sort of classical analysis. Okay. So this is a slide that you saw yesterday, so I don't want to spend a lot more time on it, but one of the pioneers in this field was the Nakamura group. And one of the nice things about this implementation is the sort of source of the magnons, which is based on the material, yttrium iron garnet, and in the very carefully made YIG spheres, which is more or less the kind of gold standard best low damping magnetic material and sort of cleanest magnon system that anyone has ever been able to find. They show really clean cavity magnonics, coupling a sphere like this, which is a millimeter-sized object, to one of these 3D cavities. You can also, as was discussed yesterday, use this cavity to mediate the coupling between one of these YIG spheres and a transmon qubit. So this is very interesting and exciting and pioneering work, but it's also limited in several ways. In other words, this sort of size of this YIG sphere means that there's a limited number of geometries that one can explore. So people, of course, tried to work with thin films. The obvious thing to do is work with YIG thin films. Again, YIG seems to be a great low damping material. It has the world record low Gilbert damping parameter, which is the viscosity parameter in the Landau-Lifshitz-Gilbert equation. Actually, the first cavity magnonics paper was this one by Hans Heubel and the Goenring group back in 2013. Later, people have made, this is a full chip of YIG on a rather large planar resonator. People have later gotten smaller, where they're able to fib out a small piece of YIG and make a transfer. These are very nice work, but what you see is that if you go from the YIG sphere, where you have a uniform mode magnon line width of around 1 megahertz, now by just going to a thin film, you see a significant degradation in the line width of the magnons. It goes to like 40 or 50 megahertz. So that's kind of one of the key challenges, is how do we make the magnetic system in a thin film geometry good enough, okay? Now, another comment that I will make is you can go to systems that are based on more patternable materials. So the problem with YIG is that it's not really compatible with the superconducting circuit parts. So you can't make sort of good superconducting circuits on top of the YIG, and separating it is a challenge. So people have taken more conventional magnetic materials like permalloy and conducting alloys that you can deposit at low temperature and do lithography on, and done these kinds of experiments. And again, this is nice, but the line widths of the magnons are even larger just because it's limited by much higher intrinsic damping. So this really sets the challenge. You'd like to have something that you can pattern, that you can control in lots of ways, but as you go towards those materials, the magnon line widths get worse, not better. So let's talk about that line width and kind of understand a little bit more carefully where it's coming from. So this is the way I would like to present this. So this is your total line width, which is what you care about at the end of the day, and it can have many different contributions. So first of all, there's what we think of as the intrinsic Gilbert damping, which in principle should be material dependent, but for a magnetic insulator, we don't really know where this comes from, and we don't really know its temperature dependence in detail. Then there's magnon scattering processes that can degrade the line width. There's inhomogeneity in my sample, so if they have some variations in anisotropy, for instance, that will lead to that term. And then there's two-level system scattering if I have paramagnetic spins that are also coupling to the magnons, which I generally do have. Let me just add a comment about the magnon scattering. It turns out that for this planar superconducting application, this is exactly the wrong configuration. So if you put the magnetic field in the plane of the superconductor, which is what you need to protect the superconductor, you also have degenerate magnon modes where you have a k equals 0 mode, the uniform mode, at the same frequency as a higher k mode. And so any kind of defect or spatial inhomogeneity in the sample can mediate a scattering that takes a magnon from the uniform mode that you're generally trying to work with to some higher k vector mode that you are not. Okay. So in order to take on this problem, we've taken a sort of a materials approach that's a little bit different than YIG. As I said, I'm collaborating with Ezekiel Johnston Halperin at Ohio State University, and he has really mastered the growth of this very kind of curious organic material, vanadium tetracyanoethylene. So this is the highest TC organic magnetic material that anyone has ever produced in a laboratory. Its ordering temperature is 600 Kelvin, which is extrapolated because if you increase the temperature to that value, the material degrades. It's above the growth temperature of the material. It has a very small saturation moment, so it's right in the range of 100 Gauss, which puts it in a very different regime with respect to, for instance, YIG, which is about 3,000 Gauss. But nonetheless, this kind of ferrimagnetic material has exceptionally narrow FMR line widths, as narrow as YIG, and in fact, its room temperature Gilbert damping parameter is the only material that is able to tie YIG for the world record lowest Gilbert damping. So this seems like a very interesting platform to move forward on these cavity magnonic experiments. So the way this material is created is it's grown in a CVD process at only 60 degrees C, which is very interesting, again, for this sort of integrating with superconducting materials that are famously not happy about being heated up to high temperature. So this is also another sort of nice property of this material. And then finally, and this is a key ingredient, Zeke's group showed several years ago that you could actually pattern this material in a lithographic way using simple liftoff techniques and some sort of chemical magic. The idea is that you do e-beam lithography of PMMA, you do the CVD growth through this PMMA template, and then you can just choose the right solvent to lift off the PMMA without affecting the VTC&E, and you can get these beautiful microstructures. I'll point out that these microstructures have sort of this lens shape to them, and that's just due to the dynamics of the gas getting in and out of this template. But crucially, as you do this, you don't see a change in the Gilbert damping parameter in FMR experiments at room temperature, again encouraging us that this is a great material. Okay, so what we want to do now is we want to integrate this material into a cavity magnonics experiment. We're going to use a lumped element LC resonator. This is just a variant of a superconducting microwave resonator that is literally composed of a capacitor and an inductor, hence the LC. So here we have this sort of interdigitated capacitor, and then the two capacitor plates are shorted by this narrow wire. And our idea here is now to just pattern this material right on top of this narrow wire, and the two systems are coupled through the Oersted field. So when we excite this thing on resonance, there's going to be an oscillating current through this wire, and that's going to generate oscillations in the magnetic material. The coupling between these two systems, this is well known. It depends on, for instance, inversely with the width of the wire, You want a low characteristic impedance for the resonator, which just means that you get more current per photon, and you want enough spins sitting on this wire that enhance this coupling coefficient G sufficiently. All right, so here's our pattern device. This is actually encapsulated with epoxy and cover glass. Vanadium tetracyanoethylene is an air-sensitive material. We heard about chromium triiodide earlier. We have the same issues here, but we can't use boron nitride as the encapsulant. The epoxy that we use is exactly the same epoxy that is on the screen of your cell phone. If you have an organic LED display that is also air-sensitive, you cover it with glass and use epoxy to protect it. That's what we do here exactly. You can see actually the bubble of epoxy front is right here, and these little squares off to the side are the alignment marks for the e-beam lithography where you expose the PMMA. So this is VTC&E. When the VTC&E is good, it's dark. When it's exposed, it turns transparent, so that's why the color change. If you zoom into this inductor wire, you can see this thing has a strip of the VTC&E very precisely patterned onto it. This wire is 10 microns wide. The VTC&E bar here is 6 microns wide, sitting right in the center. Okay, so now let's go to the experiment. And what we're going to do is start by just characterizing this microwave resonator. Now, these lumped element resonators are not known for being ultra high Q. That's not really what we're after here. And quite honestly, my group is not the best group at producing ultra high Q resonators. We're getting better, but this is some of our first results. So the loaded quality factor of this device is around 4,000. We're at a frequency about 3.6 gigahertz after the encapsulation. And this gives us a resonator line width just under 1 megahertz. And this is measured in a helium-3 cryostat, so the base temperature is around 0.4 Kelvin. Okay, so now what we do is we apply a magnetic field to the sample, and we're going to bring the magnetic excitation of the VTC&E into resonance with the microwave resonator, and we see this characteristic avoided level crossing, or this sort of separation into the two normal modes of the system that was already discussed yesterday. So of course what's happening is the resonator in principle doesn't depend on magnetic field, so it's just giving this line here, and the magnons are dispersing very rapidly with magnetic field, and so we get this avoided crossing type behavior. What's quite interesting is if we zoom in and take very careful and fine data in the region of this avoided crossing, you see there is a lot of structure going on in the sample. So you see the main mode of the avoided crossing, so this is the sort of Cattell mode of the sample, gives us this avoided crossing. But in addition to that, if we look into the details, you see these additional streaks that are kind of showing up in this data, and these can be understood as the presence of higher order magnon modes that have non-zero k-vectors that are also excited in this experiment. And I'll come back to that, but first let's talk a little bit about the analysis of the uniform mode coupling. So we do this in the very standard way. So you can think about the coupling between these two systems as just the solution of this matrix that's got, real part is the frequency and the complex part is the damping. So you can separate these things out. And so if you're sitting right on the resonance condition at this dashed line, the frequencies of the two normal modes are just the resonator frequency plus or minus the coupling coefficient G. Okay, so just by looking at these two frequencies, we can tell they're separated by 2G. So we pull this out. This is about 90 megahertz. Okay, then also on resonance, the line width of these features are just the average of the resonator line width and the magnon line width. So again, by fitting these, we can pull out that the magnon line width is about 30 megahertz, which is good, still not as low as it is in the Yig sphere case. Okay, let's go back to these spin waves, because I think there's some really interesting lessons that we can learn from this information. So first, what I'm showing you here is, again, the same fine plot, and I've put a dashed line on it, which is how the uniform mode would be dispersing if it were uncoupled to the resonator, okay? So this is the sort of, call it the k equals 0 uncoupled line. Now, from this line, we expect additional spin wave modes will go like some constant d times k squared of the magnons. And this is, for instance, describing the magnons that are quantized in the thickness of this VTC&E sample. So you have something like this, where you can have some nodes and antinodes along the thickness direction. And one thing to understand carefully is that actually the cross-section of our sample is not rectangular. It's this kind of curved shape. And so while it does go as k squared, with index they may not go linearly, or sorry, quadratically, which is in fact what you see here. Okay, nonetheless, we can analyze this situation in terms of now the n by n system, where each of these higher order modes, in addition to the uniform mode, is coupled with a G1 or G2 for each mode to the resonator. And what we expect here is that as we increase the mode number, the total effective magnetic dipole is decreasing because we have more and more nodes and antinodes being added into the system. So that means that these G sub n should be getting smaller and smaller as we go to higher orders. And so if we extend the regular input-output theory, and I'm not sure if this is showing up in this projector very well, we can reproduce these streaks just by putting these magnon modes into the model. And of course, it's impossible to fit data as complicated as these, but what we can do is characterize, try to get a good match. And what we find is that when we do that, there's two interesting lessons. So the first one is that in order to make the simulation look like the experiment, we have to, again, actually include this realistically decreasing coupling between the magnon order and the resonator. So that's good because that matches our sort of understanding from what should be happening. But the other thing that we did not expect is that in order to, again, match the data, these magnon modes have to have a much narrower line width than the uniform mode. So the uniform line width, as I said, is about 30 megahertz. But as we increase the order of the spin wave mode, we get down to about the same line width as that one gets in Yig spheres, which is very interesting. How do I know that this is actually true from the data? Is this just something that I thought of? Well, if we actually look at the fine details of this plot where these higher order modes are dispersing, you can see that they actually do have a narrow line width in the line cuts. So there's, for instance, n equals 8. Here's some of the lower modes from these line cuts. This is getting now to the signal to noise of around 2, so it's not the best data that you've seen, but they very clearly only have a few megahertz line width. Okay. So the conclusion of the narrower line width is directly supported in the data, and it implies that whatever mechanism that's limiting the uniform mode line width depends on the size of the net processing dipole, which is quite interesting. Now, I'll also note that the TLS physics, the sort of coupling to paramagnetic spins, which I'm not going to talk about, is certainly relevant here, and it is a puzzle that we're still trying to sort through and understand very carefully. We're kind of operating in the regime where KT is right around h bar omega, so this is certainly active in the physics of our experiment. 1 minute? Good, I only have one more thing to show. So I want to go back to the uniform mode again, and just one sort of maybe unnecessary but fun experiment that we did, which is to try to look at these line widths directly in the time domain, with the idea is that looking at the ring down directly allows us to look at undriven relaxation. So to do this, we do a homodyne experiment. So essentially, we split a microwave drive into a tone that we put through the sample and a reference tone, and then we recombine them on a mixer and look at that directly on an oscilloscope, okay? So we tune our system in terms of frequency and magnetic field to the working point that I show here in red. So we're sitting on one of these polariton modes, and then we can just directly see that ring down time. And so here I'm showing tau of 85 nanoseconds. This is the voltage ring down, which is twice this value. So this is the power ring down, and thus is equivalent to the damping rate that we get in a sort of the thing that we report as the line width. We can also detune either using a magnetic field or by changing the frequency from this thing. And then when we look at this ring down in the time domain, we get a beating between the actual relaxation rate of the sample and the reference tone that it excited in the first place. And so we see this coherent oscillations emerging, which is exactly what you expect. It just shows that this is, in fact, a coherent process. And we can compare these measurements with the network analyzer measurements. And of course, they agree. The line width of the network analyzer and the line width of that we infer from ring down are a good match to one another. And you can see that, again, as you get to the magnetic field where you have hybridization between the magnon mode and the resonator mode, you approach the average of their damping rates. OK. So now I am done, I think more or less on time. So what we have done here is we've taken a very different material, puts us in a very different regime, both in terms of the spin wave propagation as well as in the basic property of the magnetization, and used it to show a very strongly coupled system of magnons and photons with a cooperativity greater than 10 to the 3. We see some really interesting low damping dynamics in these systems. And the thing that gets me really excited about this is that now, because we can do lithography on the system, we're really sort of able to dream up any kind of circuit we want to do and stick magnons in it and see what happens. So that's it, and thank you for your attention.